Hello dear friends, welcome to Humble Mark Academy. In this our session guys, we shall be looking at the circuit problem we have on screen. So for instance, I got this question from one textbook I met online which is called the Fundamentals of Physics. So guys, this was among the exercises that they gave on inductor and inductance. Great. So guys, before we get started, let's introduce ourselves. I am Omenjo Macarius, and guys, this is Humble Mark Academy, where I take complex science problems, the ones that are very difficult for most students to understand. I break it down into tiny pieces such that any student watching me across the world can use these concepts now to score a better mark in his or her exam. So guys, in exchange, all you need to do is to press the subscribe button looking at you friends and turn on your bell icon to get notified so that each time I upload a video, you're going to be the first person to get notified. So guys, I can only help you to pass those your exams once you've subscribed to the channel. I cannot help you if you've not subscribed, guys. I can only help you once you've subscribed. And friends, please give the video a thumbs up. That goes a long way, friends, to motivate me to keep creating more great content for you guys. Thank you very much. Great. And friends, please go to our channel. Go through our channel so well, guys. We have enough videos there for you to help you to assist you in scoring good marks in your exam. So guys, let's dive straight into our video today. All right, so the question is saying that in the figure, the resistor R1 has a value of 8.0 ohms, R2 has a value of 10 ohms, then the inductor L1 has value 0.3 henries, L2 has 0.2 henries. Good. Then guys, and the ideal battery has EMF E, which is 6.0 volts. Then now they are saying that E, just after the switch S is closed, at what rate is the current in the inductor L1 changing? Then B, when the circuit is in a steady state, what is the current in the inductor L1? Great. So guys, it shows that the inductor L2 virtually has nothing important to play as far as the solution to this problem is concerned. So now guys, let me tell you guys how the inductor in any circuit functions. Now guys, let's take a case where a circuit has no inductor. Okay, it's a case where a circuit has no inductor. As soon as the switch of that circuit is closed, the current in that circuit just after the switch has been closed reaches its value within the shortest possible time. Okay, but guys, with the presence of an inductor in a circuit, the inductor slows the rate of growth of current in any circuit such that a circuit or a part or uh, one portion of that circuit that has no inductor in it, the current of that branch is going to approach its value within the shortest time possible, whereas the part of that circuit that has an inductor, the current in that branch is going to take some amount of time before it approaches its own maximum value. Consequently, guys, the function of an inductor in any circuit is to slow the rate of growth of current in that circuit. So now, guys, initially, just before this switch is closed, guys, the current across each of these branches has to be 0 since all of our branches have inductors, right? Great. And guys, since we have the cell here, guys, and we have the inductors, the current across each of these branches is going to be 0. That's instantaneously, guys. Just after the switch is being closed, guys, the current is going to be 0. Great. But friends, after some amount of time, we don't expect the current to be 0, right? We don't expect it to be 0. We don't. But just after the switch has been closed, that is at t equal to 0, the current instantaneously becomes 0. Great. And the reason is due to the presence of inductors. That is the function of inductors in any circuit. It simply slows down the rate at which current grows. Great. Then guys, the current eventually after some amount of time is going to build up at some rate. We can quadrate di by dt. Great. That's what we have it, friends. And now guys, since the current across each of these our branches here is 0, and we know that this EMF delivers some amount of current, right? That therefore implies the potential difference across L1 should be strong enough to counteract the EMF of this our cell, right? Namely, guys, what I'm simply saying is that the potential difference across L1 has to be the same like what has to be similar what, guys, this E, right? It has to have the same magnitude as E, but they should be in what, in different directions. Consequently, guys, what I'm saying now is that um our E in this case has to be similar like what, guys, L1 di by the T. Great. So guys, this is what the EMF across an inductor is being given as. We have the inductance of that inductor times the rate at which current builds up. So guys, if we make di by dt the subject, since that's what we have been asked to find, we are going to have E over L1. That therefore implies our E now becomes what, 6.0, our L1 is 0.3. So guys, if we plug that in and simplify, we are going to have di by dt to be 20.0 amperes per second. Great. So guys, the answer is in amperes per second, okay? Because it's a ratio of the change of current to what? The change in time. So guys, you notice that the graph of current against time, guys, is not a straight line, okay? It's not a straight line, it's a curve. Okay, I drew this graph in my previous video, guys. I drew it in my previous video, the video I uploaded before this, okay? I drew the graph. So guys, please watch the video so you're going to understand the concept so well. All right, so guys, this is going to be the rate at which the current is going to be going. So the current is going to increase by 20.0 amperes every second. Great. And friends, keep in mind that the current is going to grow exponentially. Okay, the manner in which it grows, it's exponential. So it goes in an exponential manner. All right. So now the next partner wants us to is saying that when the circuit is in a steady state, what is the current in the inductor? 1. Great. Okay, now friends, when the current in each of these inductors must have built up to some maximum value, the potential difference across each of these inductors, guys, now is what? 0. And consequently, when the inductor becomes 0 now, when the EMF across the inductor, or the potential difference across the inductor, becomes 0, the inductor L1 and this one as well becomes just what? It now behaves just like an ordinary conductor, okay? It behaves like an ordinary conductor. Consequently, guys, the voltage across this L1 is what? 0. That across this one is what? 0. And by that, guys, it therefore means that we can replace L1 with just what? A straight wire, okay? We can just complete this circuit by simply replacing our L1 with just a wire. Consequently, guys, we now have what? Just this our resistor in place, okay? Because the current now flows like this. If we consider, if we take our Kirchhoff's law, our Kirchhoff's voltage law, guys, in this external circuit, we see that since the potential difference across this L1 has to be 0, it therefore means that we are just going to have but just this our loop, okay? So guys, in this case now, we see that we just have just our EMF in this case and what? R1. That therefore implies, guys, at this point in time, we can therefore use our Ohm's law in this case now to answer it so well. By that, guys, we know from Ohm's law that our I is the same like what? V over R, right? Keep in mind, friends, I want to explain again. Keep in mind that when the current now reaches a steady value, that is when the time becomes sufficiently large, it therefore means that the potential difference across all these inductors is 0. Hence, these inductors now are behaving like what? Ordinary conductors in this electric circuit, okay? And as such, we have just what? Just our E, which is the EMF of this our cell, and what? And the resistor R1, all in series. So guys, in such a case now, we can therefore use Ohm's law to get the current that is going to be flowing through our through our L1. In this case now, guys, we are going to use the Ohm's law, which says that I is equal to V on R. Therefore means that our I becomes our V is 6 over R. Our R is what? R1, which is simply what, guys? 8.0. So we are going to have 6 over 8. If we simplify, guys, we are going to have answer to be 0.75 amps. Great. So guys, that is going to be the current that is going to be flowing across inductor L1 when the time becomes sufficiently large. So friends, that's it for our video. If you like the video, guys, give it a thumbs up and so consider subscribing to our channel if you want more great content. Stay safe, guys, and have a blessed day.